Here we are looking at L'Hopital's rule for limits that are indeterminate of the form 0 to the 0, or infinity to the 0, or 1 to the infinity. They all kind of have the same approach. And a special note here, note that 0 to the infinity is actually 0. So that one's going to be okay. That's not an indeterminate form. If that ever comes up, you're good to go. It's just 0. Well, remember to use L'Hopital's rule when we evaluate the limit flat out. We need to be of the form 0 over 0 or infinity over infinity. These are indeterminate forms, but they're indeterminate in a way that allows us to use L'Hopital's rule. And recall that if we can get it into one of these two forms, 0 over 0 or infinity over infinity, then we simply take the derivative of the top and the derivative of the bottom and try again. So our whole goal initially is to get it to one of these two forms, and there's a specific approach when we're in the exponential form, such as 1 to the infinity. That approach is to take the natural log of both sides. So it's very similar to what we did with logarithmic differentiation. Well, the first thing we do is try to evaluate this limit straight out. And if we let x run to 0 here, we get, let's see, well, 1 to the power of 3 over 0. So this is of the form 1 to the infinity, which is one of our indeterminate forms that we're looking at here. So we'll take the natural log of both sides. Well, what do you mean both sides? There's only one side here. Well, the key is to essentially forget the limit for a second and just write this as y equals quantity 1 plus 4x to the 3 over x. Now we'll take the natural log of both sides. That's a common practice anytime we have a variable stuck in the exponent that we want to get down, which is what we have here. This then gives natural log y equals 3 over x natural log quantity 1 plus 4x. Okay, so there we dealt with that. And now we'll go ahead and take the limit. So we have the limit as x goes to 0 of both sides. X goes to 0, limit as x goes to 0. X goes to 0. And remember, don't use L'Hopital's rule until you get it to the form 0 over 0 or infinity over infinity. Right? One of the biggest mistakes that I see is people trying to use L'Hopital's rule without having it in the correct form first. So let's see if we're there yet. When we run this limit through on the right, we now have 3 over 0, so that's infinity, of the form infinity, times natural log of 1, which is 0. So we're now to the infinity times 0, which is another indeterminate form, slightly better than 1 to the infinity. Well, how do we deal with this indeterminate form? Oftentimes we need to divide by the reciprocal or something like that, but here it's even simpler. Let's just rewrite this slightly, right? Let's write this, okay, we still have our limit hanging out here, limit as x goes to 0. How about if we just rewrote this as 3 natural log 1 plus 4x all over x, and try again. Okay, if I evaluate this limit, I now have 0 over 0. Check. Still indeterminate, but indeterminate of the form that allows us to use L'Hopital's rule. And remember, L'Hopital's rule just basically tells us to take the derivative of the top divided by the derivative of the bottom. Okay, so this equals by L'Hopital's rule, so I'll put a little h up there to remind me that we've applied L'Hopital's rule. Okay, we still have our limit as x goes to 0. And then 3 times, well, the derivative of natural log of all that stuff is 1 over all that stuff. So 1 over 1 plus 4x times the derivative of the inside, which is 4. All over, well, the derivative of x is 1. And now we can quite happily evaluate this limit by just plugging in 0 for x. That leaves us with 12. Okay, well, the last thing you need to do, since we took the natural log to begin with, is raise both sides base e. So our answer is e to the 12th. But I'll make a little bit more of a detailed argument here just for the sake of explaining this. So I'm going to go up here with it. So we now have the limit. If you recall, our left-hand side was the limit as x goes to 0 of natural log y now equals 12. Well, how do we undo a natural log? Well, we can take both sides base e here. But that's kind of weird because we have e to the limit. Well, e is a continuous function, so it can actually technically move in and out of the limit. So this really becomes the limit as x goes to 0 of e to the natural log y equals e to the 12th. And e and natural log undo each other here because they're inverse functions. So this gives us limit as x goes to 0 of y equals e to the 12th. But when we first started, y up here was this whole function, 1 plus 4x all to the 3 over x. Thus, e to the 12th is our final answer. So I was being very technically correct here on the left-hand side. Really, to solve these, you don't have to get too caught up with that. Just essentially take the natural log at the beginning, and then at the end, remember to raise it base e. So take your e to the power of whatever the answer you get is for your final result. So it's basically like you use the natural log and then pay it back at the end. Let's try part B. We have the limit as x goes to pi over 2 from the left, scrolling up there, kind of hard to read, of tan x all to the power of cos x. Okay, well this is of the form infinity times 0. How do I know that? Well, I carry a graph of tan in my head, as you should as well. Okay, it looks something like this, and then at pi over 2, we have this behavior. It comes up like so. It's a very rough graph, but look, as we approach pi over 2 from the left, this thing is going off towards infinity. You should also know in your head that cos of pi over 2 is 0. Right? We don't always want to be reaching for our calculators when it comes to fairly simple trigonometric expressions and evaluations. Note that Calc 2 is very trig heavy, so the more trigonometry you can get down in Calc 1, the better off you'll be in Calc 2. Okay, well, we recognize this form. This is one of those forms where we take the natural log of both sides. So let's write this as y equals tan x all to the cos x, and then take the natural log of both sides there. So hit this with the natural log of both sides. What does that do for us? It gets this cos x down to the front. Thus we have natural log of y equals cos x natural log tan x. And at first glance, it just looks like we've made things way worse. Let's take the limit right here. So we have the limit as x goes to pi over 2 from the left, which is a lot to write. Limit, and I didn't leave myself much room here either. X goes to pi over 2 from the left. And now we are of the form 0 times infinity, because natural log of infinity is still infinity. How do I know that? Well, I carry a graph of natural log around in my head, as should you. And remember, natural log looks something like this. It goes through 1, and it curves off like this, but keeps going up, up, up. So as x goes out to infinity, this goes up towards infinity. Okay, well, often when we're of the form 0 times infinity, the way out of that is to divide by the reciprocal. That's not always the case. You saw that we didn't do that in part A, but in this case it is. So which one of these terms, cos x or natural log tan x, does it make more sense to bring down as the reciprocal? I'm thinking the cos x. So this becomes the limit, still as x goes to pi over 2 from the left, of, let's bring this pi over 2 from the left. We still have natural log tan x up top, and down below we'll have 1 over cos x. Note that this is the same here, 1 over cos x. This is the same as just multiplying by cos x. Well, I'm going to rewrite this. Instead of 1 over cos x, let's just write that as secant x. Secant x. And now when we hit it, just straight evaluate the limit, we have infinity over infinity. Turns out that secant of pi over 2 is infinity. How do I know that? Well, I'm really thinking of it as 1 over cos x at this point. And since cos of pi over 2 is 0, we know we're going off to some kind of infinity. We actually really don't have to worry about whether or not it's positive or negative infinity, because we're just trying to get the form infinity over infinity. It doesn't matter if it's negative infinity over infinity. It's all the same, as long as it's the correct form. Okay, well, this is good news. We can use L'Hopital's rule. So let's take the derivative of the top and the derivative of the bottom. Note that I'm not doing the quotient rule. And try the limit again. Okay, so we have our limit still as x goes to pi over 2 from the left. And the derivative of natural log tan x is 1 over tan x. That's the natural log part. And then we do our chain rule. So the derivative of tan x is secant squared x, so times secant squared x. I love how much is going on in this problem. Divided by the derivative of secant x. Do you remember what that is? Secant x tan x. What a wonderful group of derivatives we have here. Let's simplify this a little bit. So we still have our limit as x goes to pi over 2 from the left. You have to keep writing this until you actually evaluate the limit, though it's somewhat cumbersome. We can cancel out one of these secants, so we have secant x on top over, let's combine those tans, so tan squared x down below. Well, okay, let's see here. Let's write secant, well, recall that, because I still am having a hard time really getting a grasp on what this is. Although you can do it here, but usually something like this, I prefer to convert back over to sines and cosines. So secant is 1 over cos x, and then tan is sine over cosine. So this gives us cos squared x over sine squared x. And then we can cancel this cosine with one of these cosines. So we really have the limit as x goes to pi over 2 from the left still. Although now it doesn't matter that we're approaching from the left. That's arbitrary at this point. Cos x over sine squared x. Now that's something we can evaluate. Sine squared x. Okay, well, cos of pi over 2 is 0 over sine of pi over 2, which is 1. So this whole thing is 0. So we're almost there, but that's not our actual answer. What is our actual answer? Well, it's e to the 0, which is 1. But I'll provide a little bit more of a theoretical approach to that. Remember that we had the limit as x goes to pi over 2 from the left of natural log y now is 0. So we'll take both sides base e, but e is continuous, so that moves inside the limit. Thus we have the limit as x goes to pi over 2 from the left, pi over 2 from the left of e to the natural log y, which is simply y, equals e to the 0, which is 1. And that is our final answer. So practice these, right? As with anything in calculus, the more of these that you work, the better off you will be, or the better you will become at doing them. So work through several of these examples and make sure you can do this backwards and forwards.